Is it good to take notes, this? Yeah, yeah. Is it both? Yeah, I go.
You asked me? Yeah.
Yeah.
Okay. It's a pleasure to have Bergeron today.
Okay, so recall what we have done last time. So we have constructed some co-compact lattice. Instead, here, from now on, I will only consider the group SON1, and in fact take intersection with a connected component. So recall that we have taken K over Q finite extension of degree D and totally real. And we have considered a quadratic form, Q, quadratic form in n+1 variables, and with coefficients in K, and such that for the first embedding, the signature is n,1, and for all the others, let's say it's positive definite. Then we have seen that a subgroup of, when I put a dot here, it's to say that it's a finite index. So if you take a subgroup of sufficiently big index inside SON1 intersected with the matrices with coefficients in the rings of integer, then gamma is a co-compact uniform lattice, torsion-free uniform lattice in which I will denote J from now on, this group. Okay, so that was for the construction of lattice, and the purpose of this construction is to construct special manifold, because SON1 is also the isometry that preserves the orientation of Hn, where Hn that can be described as it acts transitively on Hn, so this can be described as this quotient, and it carries so this is a hyperbolic space with a metric coming from the oh, I forgot the name. The invariant bilinear form on the killing. Sorry, the killing coming from the killing form on G, And so this is the unique invariant metric, and this is also Hn is a unique simply connected, complete Riemannian manifold with sectional curvature constant equal to -1. So we had this very nice geometry, and it was a question which is part of a larger program of Clifford and Klein. Does there exist compact manifold which can be modeled on this geometry? And this group provide example of that because Hn over gamma is are examples of closed manifold modeled on the geometry given by Hn and the group of transformation given by G. So this is the first start. There are some manifolds that are modeled on this geometry, and now I want to study their topology. What can we say about the topology of these manifolds? So there are several questions one may ask. First, do they have complicated topology? For example, what can be their Betti numbers? And we can, on the opposite, what can also ask question like, can you bound the geometry the topology in terms of geometric data, like the volume or so on? So today I want to address the first question. Can you build manifold with complicated topology with, let's say, large first Betti number? And so this is the goal today. Show that topology can be complicated. And the tool for that will be very particular to hyperbolic geometry, is the fact that Hn contains totally geodesic Riemannian, totally geodesic embedded hyperbolic space of codimension exactly 1. Which corresponds at the level of the isometric group to the fact that SON1 contains SON minus 1, 1. So this is really something which is related to the constant curvature, which is false for all other locally symmetric space. And this will be the main tool today. So the goal will be to prove a theorem of Milson. And now I will, before studying it, I will start to discuss some key part of the proof. So first, consider gamma, what I will call gamma hyperplanes. So, and yeah. So just to insist on the fact that you don't need to know much about the geometry of Hn to understand the rest. I will denote from now on X Hn. And now I want to prove a lemma, which is very close to what Pierre-Emmanuel discussed yesterday. So I will fix also gamma. Co-compact free and co-compact action. Then assume that you have what I will later call a gamma hyperplane. This is so well, let me call it now gamma hyperplane, i.e. this is a totally geodesic submanifold, so it's Hn minus 1 inside X. It's codimension 1, And furthermore, you ask that, so H is a hyperplane, and the projection, or maybe I should write it like that, the intersection of gamma with the stabilizer in gamma, oh, what am I doing? And the stabilizer in gamma of the hyperplane H, okay, acts on H co-compactly. So if you want a picture of that, think of the hyperbolic disk as the universal cover of a hyperbolic surface. What is a gamma hyperplane? It's a geodesic here. It's a geodesic here so that projects onto the surface, onto something maybe complicated. It's not very geodesic, but anyway, it's closed. It projects onto a closed geodesic. So here is what gamma hyperplane here is, and what is the content of the lemma? Then, so let me call this gamma H. Gamma H is separable in gamma. Recall that it means that there exists a sequence of finite index subgroup of gamma such that the intersection of the gamma I is exactly equal to gamma H. Okay? So this is the content of the lemma. And the proof is was essentially already done by Pierre-Emmanuel yesterday, but let's do it again. So the proof is the following. So you take let tau be the reflection in the hyperplane H. Okay. So this, because H is a totally geodesic, this reflection is an element in. Okay, I should have taken. It belongs to ON1. It does not preserve the orientation, so it's not in the connected component of the identity, but it belongs to ON1, and I can. I let gamma prime be the subgroup of ON1 generated by gamma and this reflection. Okay, this is a finitely generated subgroup of ON1, which is a linear group. So, and this is linear. So. This implies, thanks to an old and beautiful theorem of Malsev, that gamma prime is residually finite. RF. We know now that it's RF, residually finite. Okay, so there exists. So the trivial element can be separated inside this group, and now we will prove. Let's prove that lambda prime, which is the group generated by lambda and tau, is separable in gamma prime. But this will follow from the fact that now we have this automorphism, which will fix gamma prime because.
Lambda is gamma H.
Oh, what is lambda? Yeah, lambda is gamma H. So this is the third name for. He is known under a lot of names. This group. So the lambda is this one. Okay. So it's separable in gamma prime because. So let's prove it. But this follows from the fact that lambda prime is exactly the element of gamma such that gamma tau is equal to tau g. Okay, and so we could apply the lemma of that you described yesterday, which uses the finite topology. Let's do it by hand and prove that this is separable. So if we want to prove that this is separable into gamma prime, we have to take an element. Oh, let me do it here. We have to take an element in gamma prime that is not in lambda prime and find a finite index subgroup.
Which in gamma prime, right?
Yeah. Oh, yeah. Thanks. So if we want to prove that lambda prime is separable, we have to take let G prime be an element in gamma prime, which is not in lambda prime. And we want to construct a finite index subgroup of gamma prime that does not contain G prime. But if we are like that, this means that the commutator of G prime and tau is non-trivial. And of course, this belongs to gamma prime. So there exists, because gamma prime is residually finite, there exists some normal finite index subgroup of gamma prime such that G prime G prime tau does not belong to N. And now claim G prime does not belong to N lambda prime, which is a finite index subgroup of gamma prime. So why is it so? Because if you write G prime equal N lambda, then so. And here you have N lambda tau lambda minus N minus tau minus, and I'm already lost. So please help me. So what am I doing?
Maybe you want to say that lambda commute with tau.
Yeah, I want to say that. And oh yeah, it's here. Okay, thank you. I'm too close to. So this lambda commute with tau. So this is tau. So N prime and N is normal. So this is the identity. Okay. No,
this is in N, but you.
No, this is in N. Sorry, this is in yeah.
Your assumption is that it's not in N.
It's yeah. It belongs to. Sorry, I cannot do this in front of the blackboard. That's my limit, very low limit. Okay, so hopefully I'm the only one not to have understood the proof now. Okay, so this proves that this is separable. So now we can do a lot of things using separability, and that's what I want to explain. So what is the first thing I want here?
That lambda prime is separable in gamma prime.
Oh, okay, yeah. But if lambda prime is separable in gamma prime, then you intersect everything with gamma, and you end up with lambda, which is separable in gamma. Thanks. Yeah. So now let's prove a first consequence of this separability statement. Let's give name to to this quotient. So we have this compact quotient, and let H in X be a gamma hyperplane. So it projects onto the quotient into a very messy, totally geodesic submanifold. But the theorem tells you that then there exists a finite cover. In fact, it's really a reformulation of the separability, but it's a geometric reformulation of the separability. There exists a finite cover such that no, it's not completely. It's a consequence. Right? There exists some finite cover such that the projection of H into M hat is an embedded is totally geodesic submanifold. So the important word here is embedded. So let's explain what happened. So for example, I don't know, you started with a geodesic here. You started with a geodesic here, and so the whole point of Gromov's conjecture on the residually finiteness of not conjecture, a question about the residually finiteness of hyperbolic group. The whole point of this question is: if you have a negatively curved manifold, can you construct a lot of interesting finite covers? Separability allows, of course, residually finiteness allows to construct finite covers that approaches the universal cover. Separability allows to construct finite covers that can help making, for example, this geodesic embedded, where here it was not embedded. So example of such a cover, what am I doing? So I cut here. Yeah. And there are two lifts of this geodesic. One is this one, for example, and this is no, and the other is maybe I'm wrong. So let's cut it here. Does the video is turning on now? So how much do I pay if I want this to be removed from internet? Huh? Yeah? Okay. So what is this cover? You cut here, and you take the double, and now you go far from the board, and you will see that there is some lift that is embedded. My guess is that this should be this one, and there is another lift that are embedding. Of course, if you take the full pre-image, you cannot remove the intersection. But there is one lift which becomes embedded, and this is a projection of a hyperplane. So that's exactly the content of this theorem here. So let's prove now that it's a consequence of separability. Okay. So what's happening on the picture? You have gamma H, which is the stabilizer. Gamma H acts on this geodesic with some fundamental domain. But there are some, so in the geodesic, you will send this point to this point, and nothing will happen here. But there might be what I will call bad elements. And the bad elements in gamma will send this geodesic to this geodesic, and which will have an intersection here, which will create this self intersection below, because the two geodesic are gamma equivalent. So let me call let me give a name to these bad elements, and let me cheat to have the same notation. So let me say it like that. The projection of H in M is embedded if and only if the set of bad elements, which I will denote by V gamma H, and which is by definition the set of gamma such that gamma, the image of H by gamma, intersect gamma. So these are all the elements that create intersection, but of course you don't want to call bad elements the element that stabilize the hyperplane, so you remove the nice elements, which are gamma H. Okay? And so this is embedded if this set is empty. And so the goal now is to prove that passing to a finite cover, this set can be made empty. And now the lemma is the following. There exists some gamma prime, a finite index in gamma, such that the bad elements of gamma prime H is empty. Okay, so that's the lemma we want to prove. And now here is the proof. Gamma H acts on the hyperplane H co-compactly. So you can find a fundamental domain for this action. So let D in H is exactly as on the picture, where between the two dots on the red geodesic. Let D be a fundamental domain for this action. And now I will use the fact that the whole group gamma acts properly on X. And the fact that it acts properly, it's exactly, it implies that the number of elements in gamma such that gamma of D intersect D in non-trivially is finite. Okay? So this implies that there exists some bad elements B1, R, but only finitely many of them, such that the set of all bad elements, it's not only the B1, BR, because once I have a bad elements like here, of course, I could translate it by an element in gamma H, and it will also intersect. Also intersect the geodesic. And the same here, I could have translated here along this geodesic. So in fact, the set of bad elements is the union of finitely many double cosets, which is here. Okay, I can move by gamma H on the right and on the left to get back to the fundamental domain, and we have this element. But now we are in good shape because there are only finitely many elements here, so we can use the separability of the lemma I erased. Lemma. So now the separability implies that there exists some gamma prime in gamma such that gamma h is contained in gamma prime, and the finitely many bad elements B1, Br are not contained in gamma prime. So then B gamma prime H now is empty, because it's again it's the intersection of this with gamma prime. Okay. And now, since there are no bad elements, the theorem is proved and the manifold is embedded. Okay. So that's first use of separability. So we'll progress in understanding how to use the projection of this hyperplane in order to say something about the topology of the quotient. So the next step, and in fact it will be the main result today, is that not only we can ensure that the projection is embedded, but in fact we can ensure that it's non-separating. So that's the theorem. Let M here as above, let H be a gamma hyperplane. Then there exists, so it's not the same, but there exists a finite cover such that the projection of H in M hat is embedded, so this we know, and non-separating. This we want to prove. So non-separating means that if you cut along this embedded submanifold, then you end up with a connected manifold. So let's prove this. Let's prove this. So we have F. So the first theorem implies that we may assume that F, the projection of H, is embedded inside M. So we have a totally geodesic embedded codimension 1 submanifold. We may even assume, so M is, by hypothesis, M, I took it orientable. It's not, we could just have passed to the finite orientation cover, but M is orientable. Maybe F is not, but if it is not, then you just cut along F and make the double. And you get an orientable, you get the orientable cover of F inside the double of M. So we may assume that everything is orientable. Okay. So now there are two cases. One case which is very easy. M minus F is connected, and here we are happy, it's done. Okay, so now second case, M minus F is not connected. So we are in some situation like that. Our F is separating our manifold into two pieces. And let me call it left and right, okay? And the pi 1, so it's gamma, which is the pi 1 of my manifold M, splits as an amalgamated product, the pi1 of L amalgamated with the pi1 of R above lambda, where lambda is, as you remember, the second name of gamma H, which is the pi1 of F. Okay? So we have this, and we will use that there are elements, non-trivial elements on both sides. So let's call it A and B. So why is it true? So that's part of the fact that you are a hyperbolic manifold. How do you prove that there are elements on both sides? Well, one can use Borel density theorem, in fact, to prove that. Why? Because the red part is a geodesic submanifold. Okay? And so if you take the double of L, take L and glue again himself along the boundary, it's a totally geodesic boundary. So if you take the double, it's still a hyperbolic manifold. Because it's hyperbolic everywhere except maybe around the boundary, but because it's totally geodesic, you are really gluing two half ball, and the metric is glued nicely. So this is again a hyperbolic manifold, a closed hyperbolic manifold, whose pi1 is isomorphic to pi1 of L amalgamated with pi1 of L among lambda. But now this pi1 is Zariski dense in the whole group G, while lambda is being the stabilizer of hyperplane is contained in a closed subgroup SON minus 1 1. So lambda is much smaller than the whole pi1, so there must be element in pi1 of L, and of course the same gives element in pi1 of R. So that's a use I like of Borel density theorem. This show that there is topology outside something which is too constrained in a hyperplane. Okay?
So by non-trivial you mean it's more than just lambda?
It's more than just lambda. There exists elements. There exists an element in pi1 of L that is not contained in lambda. And in fact, it's so it's a infinite order element because there are only infinite order element here and so on. Okay. And so now, what's the idea of the proof? Is that because of the separability, in gamma, then you can find a finite index subgroup.
It seems to me that this is exactly where you use the codimension one of the.
No, because here even if it was.
So this is what fails for other locally symmetric spaces.
No, it's really the separability that fails for the. I mean, if you want to construct codimension one cycle in homology, then you have to have good candidates. And first, in other symmetric spaces, it's not easy to find good candidates. What are the good codimension one subspaces? And even though you had one, that then it's not because there are no more associated to Lie group. You don't have the tool to prove that the pi1 is separable. So, for example, already with a three-dimensional hyperbolic manifold, if you take a three-dimensional hyperbolic manifold where there is no totally geodesic surface, then it's easy to construct surfaces. It's easy. Yeah, you can build surfaces in that, but you are stuck because you don't know how to prove separability of the pi1, and that's exactly. if there is one thing that Danny Wise has told us in his proof of the Hagel-Wise theorem is that you need to prove separability of subgroup by other means that only algebraic way, because you limit too much the candidate as submanifold. So, that's okay. That's perfect. That's a teaser for my talk of this evening. I will explain why it's important to prove separability geometrically. But for today, we are in arithmetic. We are working with arithmetic manifold, and we are happy because we can do easy stuff. So separability is for free there. It's exactly as I think it was nice. It was really nicely pointed out by Pierre-Emmanuel. It's exactly the same with residually finite. When the group are linear, to prove residually finiteness is really easy. But what's happening when you have the pi1 of a non-positively of a negatively curved manifold? You don't know. So here we use. Again, the separability, and so there exists gamma prime such that A, B do not belong to gamma prime, and lambda is contained in gamma prime. Okay, and I want to pass to a Galois cover, so I will let gamma hat to be the intersection of all the conjugates of gamma prime in gamma, and this is a finite index normal subgroup of gamma. Okay, and now I will look at I will show you a schematic proof of the fact that now in fact the projection of H in M hat, which is X quotiented by gamma hat, is non-separating. And why is it true? Why is it true? Because take the projection. It is two-sided, so there is a left and right in this projection in the manifold. And now you can start on the right using some lift of B. But now, because B is not in gamma prime, this is certainly not in gamma hat, then it goes from this point and go to another connected component of the projection. So you have this. And now you go from the left to this. But now you use a lift of A, alpha. And you keep going on like that until, because it's a finite cover, until at some point you go back where you go back to so you are here, right here, and then so let's say it's left here. Okay, then you have to go back left. You cannot. You don't go back here. But you go back. I don't know, somewhere here. And if you take the whole. This combination of lift of alpha AB, 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 it intersects this projection into exactly one point. So there is a loop in the finite cover that it intersects the projection in exactly one point. So this projection is non-separating. And of course, if one projection is non-separating, all the others are also non-separating because you took a Galois cover. Okay, so that's a bit fast, but that's the way to use separability to prove the non-separating statement.
It was a bit fast.
It was a bit fast. Huh? Okay.
It was a bit slower.
Okay, I can try to say it better. No, better. Well, am I able to do that? Let me let me. So let me look how I decided I should say that. Yeah. So you have this finite cover that I just described, and here you have the different connected components of the preimage of F here. So there are a finite number of connected components. Okay. Now now if you take a lift of A, okay, a lift of A, before passing to these covers, maybe consider this one. A does not belong to gamma prime. So it means that the lift with respect to the base point, be careful here, it's not a Galois cover, but you take the base point, there is the lift goes from F, the projection corresponding to lambda, to another projection. Now if you pass to a Galois cover, it means that each lift goes from one connected component to another. Really distinct connected component. So you will lift a loop of the form A, B, A, B, A, B. At some point, there is, because it's a finite cover, there is some power of AB that gives really a loop here. But each A and B goes from one connected component to another. Okay? So you look at you start with the base point, and you look at your first connected component, F1 hat. Okay, you use the lift of A, which I call alpha because it's a lift. It goes to a distinct connected component, F2 hat, and it stays on the same side. Here, let's say I was left, so it stays on the left side of all the connected components. Okay? So now beta is on the right side, but goes to another connected component that cannot be the same as this one. And you go on. At some point, you will have to come back to a connected component before, and this cannot be this one, because we know it has to be another different connected component each time. So at least it goes back to one of them before, and I don't know where exactly, but I don't care because the whole loop you see there intersect this connected component in exactly one point. And so if you cut along this connected component, there is one connected. You obtain a manifold which is connected because you can go from one side to the other. Okay, so that's the proof of the non-separation. And now, what time is it? Okay. Okay. Now let me state a better theorem. And be even quicker. So let H be such that there exist now two projections of gamma and of H and a translate of H, or if you want two elevation of the projection here in that finite cover, two projections, which I will call F1, F2, embedded in M hat, and such that if you remove F1, the reunion of F1 and F2 in M hat, then it's still connected. So now you now you end up with two projections like this, which whose reunion does not disconnect your manifold. And the proof is really similar. Because what can happen? Now we know that we can suppose our manifold is non-separating. So we are in the following situation. Let's say we have M, and here. Okay, I lost the red. And here you have the result of the preceding theorem, a non-separating F. Okay, but here again, using the same trick with Borel density theorem, for example, you know that you can. So first, I should say, first we know that there is an element like that with intersection 1 because it's non-separating. But using now the same trick, but instead of amagnetic product, you have HNN extension. You can find an element which has trivial intersection with F, but which is non-trivial in the group. So here again, it's of course it's false in a torus. So here again, you use hyperbolicity. And now you play the same game with the green and the blue element. You take lift. So let me draw the picture, the symbolic picture. You take lift, and so let's say it's minus plus locally, and you take the blue one. Oh, I'm always. One of them has a trivial intersection with the red curve.
The red is F.
The red is F. Yeah. F. For the moment, there is. This is the result of the.
And the others are a loop.
Yeah. F is a manifold, and the other are loops. And for this here at this stage, I am in the result of the preceding theorem. So F is embedded and non-separating. Now I say that there is, because it's non-separating, there is this blue curve with intersection 1, and because the manifold is complicated, there is also an element which has trivial intersection with F, but which is the non-trivial element. And here again, I use separability, and let's say we have this side is plus and here is minus. Then we lift the green to another component. So now it's plus minus here, and now you use only blue lift. Okay. So each time you change like this, and at some point you have to close. But so because it goes from one unconnected component to another, you have to go to I don't know, somewhere before here. And the good point is that you find this blue curve that does not intersect the first lift here, and that intersection 1 with this one. And that gives you that the reunion of these two does not disconnect the surface.
Why don't you return to the beginning? Why can't you return to the beginning?
Why?
Why don't you return to the beginning?
I don't return to the beginning. That's a good point. Let me remember. So, what am I saying? What? Wait. I've said something stupid. No. Sorry. There is a.
No, the beginning is plus minus.
It's plus.
Just here.
Oh, yeah.
Your signs are.
I know, but the green.
Wait. The- what am I doing? So yeah, I made a. So here is minus plus. You leave. No, that's strange. I cannot reconcile what is. Okay. Maybe okay. Maybe I'm wrong in the. Oh. What am I doing? Okay, let me correct this soon, but not now. I have to. No, maybe I'm mixed up with the blue and the green, but I want to finish. So trust me for the moment. I owe you this next time, and it's just a matter of bad preparation of my talk.
Don't you end up always with a class? Each step?
No, because you leave the blue one change the sign, and the green one preserve the sign. So you have to play with this, and so maybe okay. Let me try. I made a stupid mistake, so maybe it's on this side. I have to. Where?
Nicolas, so you have some H&N extension or
Yeah.
make a product so it's act on a tree and you can
Yeah, but I
put it all game in the tree?
Yeah, you could use this. So I will say this was used by Alex, in fact, to give a proof of that. But I wanted something very explicit where you can find the two embedded surface that are non-separating. So just this should work. This work, I'm sure. But I just have to remember what am I doing. So if I take the blue, no, sorry, I don't. I will lose too much time now. So let me think of this and I explain this tomorrow. Sorry, but I wanted to conclude from this that as a corollary, if there exists gamma hyperplane, then gamma virtually, meaning that there is a finite index subgroup of gamma that surjects onto the free non-abelian group of rank 2. So this was, so this, under that form, this is due to Lubotsky. And as you say, using the H&N extension and the action on tree. But so how can you see that from the construction? If you have two non-separating hypersurface in your manifold, so you have some kind of picture like that. You have your two non-separating hypersurface, F1 and F2. Then you can take a tubular neighborhood of these and retract everything outside the tubular neighborhood on a point and send the curve transverse to the surface to a loop. So this gives a continuous map to this, and this continuous map gives you the surjection of the pi1 of this manifold to the pi1 of this bouquet of circle, which is the free group. And once you have that, then instead of keeping proving theorem with F1, F2, F3, F2, etc. You can just use that in the free group. There are finite index subgroup that are free group of rank arbitrarily large, and so you have a surjection of finite index subgroup of gamma onto free group of rank arbitrarily large, and in particular you have the first homology, which can be of rank arbitrarily large. So in that way, you obtain that if you have gamma hyperplanes, then the homology can be as big as you want. And now to conclude, I should say that for the arithmetic construction I have described last time, there are always gamma hyperplanes, because if you have a quadratic form of the form if it satisfies the if it's a quadratic form defined over a number field and satisfies the hypothesis I've said at the beginning of the hour, if you forget about the first coordinate, then you have a quadratic form in n variables of signature n-1 at one place, and this gives you a gamma this shows that the stabilizer of some hyperplane is also an arithmetic subgroup, so acts co-compactly on this hyperplane. So all the arithmetic lattices I have described at the beginning, in the first lecture, they have gamma hyperplanes, and so you obtain the following theorem of Nielsen, that if M is an arithmetic manifold, arithmetic hyperbolic manifold of simple type, because I should say that there are other arithmetic manifolds that I haven't described. So the one I have described are called of simple type. Then there exists for any n, there exists some cover M hat, finite cover of M, such that the first Betti number of M hat is larger than M. Okay, and I think it's time for me to stop. So sorry for that. I will describe this. I will come back to this tomorrow, not tomorrow, but next time. And I will explain now more things about possible topology of hyperbolic manifold.
Where did you talk? In all of the description, I didn't see any numbers. Why are you talking about arithmetic?
Why am I talking about arithmetic? Because I need hyperplanes. I need gamma hyperplanes. And so there are two answers. First, we don't know much non-arithmetic manifold in higher dimension. In some sense, there is this very nice thing that the only negatively curved manifold we know of dimension, let's say, bigger or equal than 5 are essentially arithmetic or surgery on arithmetic manifold or bumping the metric, this kind of stuff.
But all of them,
Huh?
those examples of Montefiore Shapiro do have, in fact, the proof works for them.
I say essentially up to surgery. So there are non-arithmetic manifold in any dimension constructed by Gromov and Piatowski-Shapiro, but they do surgery. They take two arithmetic manifold, they cut along totally geodesic submanifold, and they glue them. So for them, all what I've said applies. It applies to arithmetic manifold, and I insisted on arithmetic manifold because that's the.
What did these guys proved recently with dynamics?
Karl-Markovich. So it's purely three-dimensional, and in dimension 3, then you can construct a lot of surfaces that are almost totally geodesic. But they are not totally geodesic, so you cannot prove separability just using algebraic method. And to prove the proof by Argyle-Wise that everything is true for the Betti numbers and so on uses to prove that you need to prove separability of almost geodesic surfaces. But to prove this, you need geometric method because algebra is not working anymore. And I will try to explain this geometric method in pictures tonight. So yeah.
So do you have Even one example where this fails, where the conclusion fails.
Well, the conclusion fails, no, but we can prove with, so in dimension 7, so in dimension 7 there are particular arithmetic manifold which is related to triality. And then all the, for them, the congruent subgroup problem is still open, so we don't know if there are not congruent finite covers. But what is sure is that for congruent covers, the first Betti number is always 0. So that's, and now that's a question of what should we believe. I think usually geometer tends to believe that this should always hold. Danny Weiss, for example, is sure that this is always true. I'm not sure. I'm not so sure, but I won't take the risk to bet against Danny.
Conclusion or the existence of
The conclusion.
dimension 1 closed sum manifold?
Oh no, codimension was closed sum manifold. There are examples where there are none. But this conclusion, you may wonder if it's true or not. This is a conjecture which is attributed to Thurston, so it's not clear. Thurston really thought about higher dimension.
Okay, let's thank Nicolas.